This lesson deals with the maximum real power transfer theorem. You can find these notes in the ECE202 ebook in chapter 16, starting on page 20. In our last video, we took a look at a series of examples where we were able to increase the efficiency of a system. We had a similar idea in ECE201. Also in ECE201, when we're looking at DC circuits, we found that there was a way to maximize power transfer when you had a Thevenin resistance. There's a similar theorem for AC circuits. Stated as following. A source with a fixed Thevenin impedance, Z Thevenin, delivers maximum real power to an adjustable load, Z sub L, when that load is the complex conjugate of the Thevenin impedance. Now, why would that be true? Well, let's draw a circuit. Here we've got a Thevenin equivalent circuit with V Thevenin and Z Thevenin. The impedance here we'll write as having a real and imaginary part, and likewise for our load, a real and imaginary part. And now we'll start to calculate the power in the load by using the value of the current that's here. The real power delivered to the load is a magnitude of the current squared times R sub L, which is the real part of Z sub L. So what's the current? Well, it's simply the voltage divided by the total impedance, which is R Thevenin plus R sub L plus J X Thevenin plus X sub L. Right, the magnitude of this is going to be the magnitude of this squared, so then square root, we're going to square it again. And likewise here, the magnitude of this is the square root of the real part squared plus the imaginary part squared. We're going to square that. So we get the real part squared plus the imaginary part squared plus the magnitude of the numerator squared times R sub L. Now let's write the denominator as just simply that raised to the minus 1 power. We have a product of terms here. If you remember back in ECE201, we talked about how to find a maximum value by using the second derivative test of calculus. To do that, you have to find what are called critical points. This is taking the variable you're trying to maximize or minimize, and to take the first derivative and to set it equal to 0. We're trying to maximize the real power to the load. That's a function of two variables. It's a function of R sub L and X sub L. So we'll take the partial derivative with respect to that. I've written this as a product of terms. You can use the product rule in taking the derivative and also the chain rule. So let's see how to do that. We'll take the derivative of this with respect to R sub L. So I have a product of two things here. This is R sub L and this is R sub L. So the derivative with respect to R sub L is going to be the derivative with respect to this, which is just going to be equal to 1, then times V Thevenin squared times the remainder here raised to the minus 1 power. Then we have to take this quantity and then take the derivative of this. So I get V Thevenin squared times R sub L, and then the derivative of this with respect to R sub L, we can use the chain rule. So minus 1 in front, then this quantity raised to the minus 2 power, and then the derivative inside here, we again use the chain rule, because I got R sub L here. It's going to be 2 times the quantity R sub L plus R Thevenin to the first power, reducing this by 1, and then the derivative of what's inside here with respect to R sub L, which is just equal to 1. Of course, the derivative of this with respect to R sub L is equal to 0. So let's put all this together with a common denominator. I've got this term raised to the second power, so I'll put that in the denominator as squared. And now this quantity here, I have just raised to the first power, so let's multiply this by this quantity raised to the first power divided by raised to the first power. And then the denominator would then be squared, and then I have one of these in the numerator. So here's that term times V Thevenin. And then I have from over here, I've got the V Thevenin squared. I'll pull that out in front, and I've got an R sub L, a 2, and the quantity R Thevenin plus R sub L to the first power. I also have a minus sign here. And then the denominator. Set this equal to 0 to find the critical points. Now I also have the reactance part of our function, so let's take a derivative with respect to X sub L. Let me go on top here and let you look at this way. I go take the derivative from my function P sub L. I only have X sub L in this quantity here, so it's going to use the chain rule. So I have a constant in front. This quantity then raised to the minus 2 power, and then take the derivative inside here with respect to X sub L, which is going to be again chain rule again. So I'll have a 2 times this quantity raised to the 1 power, and then inside of here, the derivative with respect to this is just equal to 1. And this is shown here. So here's my quantity raised to the minus 2 power. I brought that minus 1 in front, and then I took the derivative of what was inside here. So I've got this term with a 2 in front, and reducing it by 1, and then the derivative inside was just equal to 1. So I got this as our denominator, and then our numerator is a minus V Thevenin squared 2 R sub L. Here's a 2 here, and here's R sub L, and then the quantity X Thevenin plus X sub L. Also set that equal to 0. In this last term, setting that equal to 0, we could do that by making X Thevenin equal to minus X sub L. And if we go back to the previous formula over here and use that same fact, then this term vanishes, and I have just this term here left over. Setting that equal to 0, then this quantity would have to equal this quantity. And that's what's shown on the next page here. So dividing through by one of these quantities, that gets rid of this, and it gives me a 1. So I get R Thevenin plus R sub L is equal to 2 R sub L, and that just implies then that R sub L is equal to R Thevenin. Okay, so now we have the critical points occurring when X sub L equals minus X Thevenin and when R sub L equals R Thevenin. I would take the second derivative with respect to X sub L and R sub L, and then put these critical points in. If the resulting calculation is less than 0, then we have a maximum. But we already know a maximum exists in playing with our systems, and so we could skip taking that second derivative test. That's being an engineer versus being a mathematician. And this is the proof of the maximum real power transfer theorem.